In this final short video for this session, I'm going to give you a bit of a comparison then between the properties of conditional and unconditional mutual information, and then talk about some further features before wrapping up. So starting by comparing what we get from a conditional mutual information to an unconditioned mutual information. The conditioning can change things in a few different ways. So firstly, it could actually have no effect at all if the variables are all independent, for example, or simply if there is an independence of the relationship between x and y from z. On the other hand, the conditioning on z could actually serve to decrease the conditional mutual information in comparison to the mutual information itself. This can happen where y and z carry what we call redundant information about x. That means that z has already explained away some of what could have been detected by y about x. An example here is if x, y and z are all copies of one another, and if we assume that they're all IID random bits, then we would have a conditional mutual information of 0, even though there's actually full information of 1 bit mutual information between x and y. A third possibility here is that the conditioning on z could actually serve to increase the conditional mutual information in comparison to the unconditioned form. What we say has happened here is that y and z together provide synergistic information about x, which cannot be detected by examining either alone. The classic example of such synergies is the exclusive OR function. Let's say that x was the result of an exclusive OR between y and z. If we've got IID random bits, then we will have that the conditional mutual information between x and y given z gives us 1 bit, even though the pairwise mutual information between x and y gives us 0 bits. We can see it's quite clearly from an exclusive OR. As I say, if these are IID bits, knowing y on its own won't tell us anything about x. But if we already know z, then adding that knowledge of y gives us everything we need to know about x. Okay, that's a synergistic relationship. So here, the classic way people used to look at these increases or decreases was to simply take a net of those terms, and we call this net synergy. This difference or a negative value of it have been known by various names over the years, including co-information, interaction information, integration, and so on. Whatever you want to call it, what's clear here is that if this term is positive, it implies the presence of synergy, or if it's negative, it implies the presence of redundancy. That's just an implication though. Importantly, we want to think about the possibility that we could have both redundancy and synergy at once. Okay, they could both actually be present, even though taking a net of these terms here may only imply the presence of one or the other. This has led to a very active area in contemporary information theory, known as information decomposition or partial information decomposition. The reason this area has been so active is because we can't measure redundancy and synergy with traditional measures from information theory. We can represent this diagrammatically thanks to Williams and Beer. We could look at the whole information between two sources about a target, here represented in the outer oval in this kind of Venn diagram like diagram. We call this a partial information diagram. We could then look at within that the information from source 1 about the target and the information from source 2 about the target. And we can imagine that there is something redundant that both source 1 and source 2 are telling us about the target, that maybe there's something unique that we can find out from source 1 only about the target, something unique we can find out from only source 2 about the target, and then a synergistic piece that we can't find out from either target alone but need to put them together to find out about the target. So as I say, we only have these 3 measures from traditional information theory about information, but there may be 4 terms that we want to measure. So we have a fundamental algebraic problem. So there's been a lot of work going on in contemporary information theory to try and get a new measure for redundancy that can lock in all these pieces in the diagram. What those measures are out of scope for our current course, but if you want to read about them, you could look at this editorial for a special issue that we wrote in 2018, and indeed the work of my PhD student Connor Finn, which I think is giving us the right measure, or the right approach to use for finding redundancy using a pointwise approach. Moving on though, the next thing I want to highlight to you is we can see a chain rule for information now. If we think about having a number of sources and one target here, we can think about chaining the information we get from one source first, from a mutual information term, plus information from the second source, conditioned on the information we got from the first source. The conditioning is important because it makes sure that we don't double count the same information from Z that we've already counted from Y in the first term here. And of course we can reverse the order and get exactly the same final result if we reverse the order of Y and Z that we consider here. This chain rule generalizes to a multivariate set, however many n terms you might want to have. You can do the chaining in the same way by considering your terms in order and conditioning on the source terms that you have already considered. And we can look at this as an information regression, regressing the information that we find in our target across these source variables. We can write the chain rule in a very similar way for pointwise terms as well, of course. So a final aside that I want to give pertains to deriving mutual information. I've kind of laid it down as a given in this lecture, coming from various aspects of intuition, but it turns out we can actually derive mutual information directly from axioms in the same way that we derived entropy from axioms. The approach that I really like for this is found in the classic Fano text, which looks at deriving first the pointwise mutual information and then implying the average mutual information as an ensemble average over those terms. So Fano derives the pointwise mutual information as the unique form that satisfies 4 particular axioms. It satisfies once differentiability across these probability functions. It satisfies that the conditional form matches the unconditioned form, but simply with the probability distribution functions conditioned on Z. It satisfies a chain rule or additivity. Okay, as we just looked at, it was a very important property for us to consider, and it satisfies a separation for independent ensembles here. So if we have X and Y being independent of U and V in the joint probability, then we can consider the information between X and Y UV as being summed to get back to this mutual information term between 2 pairs of variables. Okay, so to summarise what we've done in this session, I've introduced you to the ideas of uncertainty and surprise. So coming back to this key notion that we have a way of measuring uncertainty and we have a way of measuring a reduction in uncertainty, and that's the reduction in uncertainty that is what we mean by information. Information is uncertainty reduction. Information and uncertainty are 2 sides of the same coin. We now know how to calculate all the fundamental measures of information theory. We know how to calculate entropies, information terms and their conditional forms. We know how to calculate these from PDFs, and from our activities we know how to do this empirically from data. Coming up in the course, we're going to be moving on to a much more advanced toolkit. Instead of doing this in the rudimentary way we have for discrete valued variables, we're going to use a much more advanced toolkit, and that will allow us to deal with continuous valued variables as well, using a number of different estimators, and we'll look at these aspects in the coming sessions.